All right, good morning. Good. Today we're going to continue with the same section we were looking at last time. This is 12.5. We'll look at a few more, somewhat more complicated quadric surfaces. And it's important that you're able to at least visualize what these surfaces look like, because later on we'll be doing calculus with these things. So it's very important that we can at least get some kind of idea what these things look like. Last time we saw a couple examples. We saw cylinders and we saw an ellipsoid. And we'll continue with a catalog of shapes. First of all, a quadric surface in general is of the form ax squared plus by squared plus cz squared plus dxy. And you get the idea after seeing a few of these terms. This is the most general case. All right, so, and then A, B, C, D, E, these capital letters are, of course, constants. The key part here to remember is that these things can have at most square as their power, second power at most. They can show up like this, x, y, y, z, y, x, z. And of course, they can show up by themselves. And of course, a constant can also show up. But the most important thing to keep in mind is that at most, a second power in each variable. All right, so let's start with this first example. Minus x squared plus 7y squared minus z squared is equal to 7. And let's find out what this thing looks like. Okay, last time, if you remember, we used traces. We essentially found slices of each of these things and then stacked them together to, yeah. Did I skip G? A, B, C, D, E. I did skip G. Yes, it goes right here, right? G, X. All right, sorry about that. There, that looks good. Okay, now we're going to use the same thing, the same technique we used last time. And remember, what we do with traces is to let x, y, z be some constant, let's say k, and then we stack together the cross sections. All right, so let's first start with z is equal to k. You can start with any variable, but starting with z is a good idea because then you're working with x and y, and it's usually easiest to recognize shapes in x and y for most people. All right, so for some constant z is equal to k, the shapes that we'll be dealing with are minus x squared plus 7y squared equal to 7 plus k squared. Right? Remember, z becomes a k, a constant of our choice. It goes over to the other side, so we have 7 plus k squared. What shape is this? I heard ellipses, I heard the parabolas, hyperbolas, that's right. See, these things are squared, and one of them is negative. This means we're dealing with a set of hyperbolas. If these are both squared, then what do we have? Both positive, then what do we have? Ellipse, right. What about if they're both negative? Probably an ellipse, you can just factor the -1 to the other side, and then you got to worry about that number. But that's a different story. For right here, we're dealing with a set of hyperbolas, right? Minus and plus. Different signs here means we have hyperbolas. All right, so in the x and y plane, for some chosen value of k, all right, so notice what happens if y is equal to 0. If you make y equal to 0, then you have a negative quantity equaling a positive quantity. Sum of a square number plus a positive number. This is always positive. But this right here is negative for any x. So this cannot happen. This cannot happen for any x. This is telling you that the hyperbolas have no x-intercepts. It is not allowed to cross y equal to 0. So what that tells you is that the hyperbola must look something like this. It must intersect the y-axis. And of course, hyperbola has 2 branches. Okay, let me write that, we just discovered there. This cannot intercept x-axis. Because minus x squared equal to 7 plus k squared has no solutions for any value of k. Right? A negative thing cannot be equal to a positive thing for any value of k here. What happens when we change the value of k? What happens to this hyperbola here? Is it always going to look like that? Yeah, that's one thing. What else? What else can change if I change k? The vertices, the interception here. See, if you make x equal to 0, changing value of k here is going to give you different values of y. So it's going to change the size of the hyperbola and also going to change where they intersect the y-axis for different values of k. But it'll stay mostly that kind of shape. Okay? Okay, so that's one of the perspectives. This is the shape that will be, this is the surface this is what we will see if we look from the top down. From this view here, the z-axis is coming straight out at us. So we're looking at this thing from the top down. Next, let's look at what happens if we let y be k. And now we're looking at this shape from one of the side perspectives. If y is equal to k, then the equation can be rearranged minus x squared minus z squared is equal to 7 minus 7y, k squared. And here we have a subtraction here. Let's take the minus sign to the other side. Okay? Okay, so now what shape is this? Right, we got a bunch of circles. What's the restriction on the value of k? K squared has to be greater than or equal to 1, right? So that means, let's write that down here, k squared greater than or equal to 1. If k squared is equal to 1, then we have a dot, and that's okay. But anything, if k squared is less than 1, then this is negative, and we can't have a circle with a negative radius squared, right? So we don't have that shape. Now, exactly the restriction on k is not too important at this point. Right now, we're focused on getting the shape of this surface. Okay, now let's sketch the same kind of perspective we got in the last step. We're looking at x versus z. In this perspective here, where is the y-axis? Is it coming out at us or going into the page? And how do we know? The thing you're doing with your hand is perfect. The right-hand rule, right, that's right. The y-axis is into the page. Remember, we got to obey the right-hand rule. Now, if you have trouble seeing that, just look at the regular XYZ perspective we draw all the time. Right? In order for X and Z to show up like that Y has to necessarily point into the page. So that's the perspective we're looking at from the left side of this shape. Does that make sense? Yes? Good. And we're dealing with circles. We know what circles look like. We may not be able to sketch it very well, but that's what we got. At different values of k, of course, we'll change the size of that circle. But the center will always remain on the origin. All right, now let's look at the last perspective. Now we're looking at x is equal to k. And the original equation rearranged a little bit. We get 7y squared minus z squared is equal to 7 plus k squared. What shape is this? Hyperbola, good. Which axis do the hyperbolas intersect? Y, right? Because if you let y be 0, you get negative equal to positive. That can't happen. So therefore, it tells you that the hyperbolas have to intersect the y-axis. All right, we're looking at y versus z now. So y here and z. And where is the x-axis? Coming at us or away from us? Right, coming straight out, right? Looking at this perspective here again, yz, we're looking at front, back. So x is coming straight out at us. All right, so the positive variable tells you the intersection locations. This must intersect the y-axis. Something like that. Any restriction on k here? Can k be any number? What do you think? Yeah, the right-hand side is forever positive regardless of the value of k. So you have 7y squared minus z squared is equal to some positive number. That's always going to be a meaningful hyperbola. It'll change the size and the location of the interception, but it's always going to look something like that. Gets bigger, smaller, shifting left and right, but always the same kind of shape. Okay, let's put this together now. And I'm going to resketch the perspective views on the same page here just so we can keep referring back to what we should be seeing. So I'm just reproducing what we already know. That's z is equal to k. Y is equal to k. We get a circle. And that's a good circle. And last, the x is equal to k. We're looking at y versus z now. And this time we have hyperbolas that are open left and right in this perspective. Okay, now we put this all together. This one here is what we will see when we look from the top down. So imagine we're hovering above the xy plane looking down. We see this. What that means is that on the x and y plane, we're going to see this kind of thing. Right? Looking down, we're going to see that projected onto the x and y plane. Looking from the side, so looking from this perspective at x versus z, we see a circle. And what that's going to tell us is that this must be what we'll be seeing if we have a surface that's revolved using that shape. So that's the first clue we have as to what shape we're dealing with. This side view here. We must be looking at something kind of like that. And from the other side, of course, we're seeing the same kind of circle. Something like that. Can you visualize that? Yeah? Now these cross sections that we're seeing, lastly, y versus z. Now we're looking at here, looking down, and we're seeing this, and that makes sense. Yeah? This is the side view that we should be seeing. So where do these things show up here? The circle, of course, happens at any y that you choose. If you choose any value of y, you're going to get a circle of certain radius. That's what we're seeing here. If I choose any value of y, we get that. Right? So that's the thing we'll be seeing looking at the side at this hyperbolic kind of shape. Looking top down, we're seeing two hyperbolas. And what we're seeing here, top down, are these things. Right? If you choose different values of z, each time I slice, I will see two hyperbolas of different size, and the location of the intercept with the x-axis the y-axis will be different depending on the height I choose to slice at it. And then finally, this front view here, we're seeing, of course, this kind of an outline here. Kind of like that, right? So the traces tell us the different slices that we'll see. You can slice parallel to each surface, and that's the same meaning as letting x is equal to k. X is equal to k means we slice parallel to the yz plane at an x value of our choice, and we'll see that. Y is equal to k means we slice parallel to the x and z plane, and we're seeing circles. That makes sense. And finally, the top view, same idea. Does that make sense? Yeah? How we went from the perspectives to this? Yeah? And the shape, this shape here, this is called a hyperboloid of two sheets. Because what happens here is we have two detached parts to that surface. We call that a hyperboloid of two sheets. Questions? Okay, now the next example here, I'm going to change the sign of a couple of these things. So, and we'll see what happens when we do that. This time I want x squared to be positive, I want y squared to be negative, and a positive z squared. Last time we had negative plus negative plus. Now we have plus, minus, plus, plus. And we'll see what happens. We expect kind of the same shape, but there's a sign change in two of these variables. So something must be different. Same process. You take slices that z is equal to k, x, y is equal to k, x is equal to k, and then stack them together. All right, so we know how to do this. We have x squared minus 7y squared is equal to 7 minus k squared. Shape. Right. What axis do they intersect? If 7 minus k squared is positive, then the hyperbolas will intersect the x-axis, right? Something like this. But now notice that if we keep changing k, and 7 minus k squared turns out to be negative, then what happens? Yeah, these will get rotated, right? So this, if 7 minus k squared is negative, then we get a bunch of those things. That's already going to be a little complicated when we get to sketch this thing. But let's just leave that for now. look at what the other perspectives tell us before we worry about that situation. Now let's proceed on to y is equal to k, and we get x squared plus z squared is equal to 7 plus 7k squared. And we've seen this before. It's the same y is equal to k shapes as the last example. Circles, right? Circles. And regardless of the value of k we choose, we still have circles. The only thing that's going to change is the radius. There we go. That's what we get. And that's great. That's a very simple perspective to have. Okay, now let's look at x is equal to k. Letting x be k, we get negative 7y squared plus z squared. Oops, sorry. Seven minus k squared. Different signs. So again, we have hyperbolas. And now we're looking at y versus z. And x is coming out at us, the usual perspective we just saw. Okay, now assuming that 7 minus k squared is positive, z is positive, is telling us that the hyperbolas will be on the z-axis. And if 7 minus k squared is negative, then this will be switched over to lying on the y-axis. All right, now putting this together, this is going to be a little bit of more work than the last one. Looking at the first slice, the first set of traces, z is equal to k. This is when we're looking top down. And 7 minus k squared greater than 0 means we're looking at the portion including the x and y plane. That's when k is equal to 0, right? So just the portion near the origin. And that's a good portion to start. Start with that portion. Okay, top looking down, we're seeing hyperbolas that look like this. That's going to be on the x and y plane. Then y is equal to k means we're looking from the left side again. And we're seeing a bunch of circles. So that's going to tell us that we're dealing with some kind of revolution, just like in the last example, something like that. Then finally, looking at y versus z now, we're seeing this. So that's going to so imagine looking from parallel to the x-axis, looking at the y versus z, we're seeing this near the origin. So that must be what we're seeing here if I fill in the shape. That's a very good sketch, if I say so. Look at that. This is beautiful. Okay, so it's kind of like, it's not quite an hourglass. I guess this could be like an apple core after you've eaten the apple around it. Something like that. Kind of a, I don't know what else you can call this thing besides its technical name. It's again a hyperboloid. Now this oid ending here, you take a shape you already know, you put an oid ending to it, that means we're dealing with some kind of three-dimensional extrusion of the shape that you're used to seeing. Hyperbola with a loid at the end must be a three-dimensional hyperbola of some sort. Now this is not detached like the last example. Last example we had two separate pieces. Here we have one piece. This is called a hyperboloid of one sheet. Okay? And so that's the difference between the one sheet and the two sheet here. It's the same outline, the same traces, the same outline. But the difference is which outline defines the enclosed portion of the surface. All right, we got a couple more shapes to look at. The next one, now we're going to make one of the variables not squared. We'll leave two variables squared and one of them not squared. X squared minus y plus z squared is equal to 0. All right, so when you have one of the variable is not squared, if one variable is not squared, solve for that variable, and this is called a standard form, if one of them is not squared. If all three are squared, then there's only one form that you could deal with. Okay, now we do the same thing. Take slices of that again. This will be a little bit easier than the last example. If z is equal to k, some constant k of our choice, we get x squared plus k squared. And what are these? What shape? Parabola. Which way does it open? Well, I guess we need to sketch the axes first. X versus y here. Okay, now we can say this question makes more sense now. Which way does it open? Up, right, because x squared is positive. opens to positive y. And what does k do to the parabola? Very good. It changes the vertex of the parabola, sorry. So this is when k is equal to 0. If k is equal to plus or minus 1, for example, it might look like that. And notice that we can never make k squared negative. That means I cannot make this parabola go below the x-axis. It is forever constrained to be above or on the x-axis, right? K squared is never negative. Okay, looking at y is equal to k, what do we get? We get x squared plus z squared is equal to k squared. These are circles, right? Circles with radius k, centered at the origin. Origin here meaning x equal to 0, z is equal to 0. And different values of k will change the size of the circle. Okay, so we did z and y equal to k. Lastly, let's look at x is equal to k. And we get, what do we get? We get y is equal to z squared plus k squared. And these are the same shape as z is equal to k, right? Same idea. But let's see what they look like. Y versus z, let's put y here, put z here. This means x is coming out at us. Y is equal to z squared. Now, which way do these parabolas open? To the positive y, right? Y is equal to z squared. Means that you have symmetry with respect to z. So this opens to the right, to be more precise, positive y direction. And as usual, k squared can only be positive. This means that the vertex can never be brought to the left of the z-axis. K equal to 0, k is equal to plus and minus 1 might be this, plus and minus 2 will be further to the right. Okay, now we stack them together, starting with the top-down kind of view here, looking from above, looking down at the x and y plane. We see on the xy plane, we see a parabola with a vertex at the origin. Yeah. Which way? On the previous slide, okay. Under that would be k, yeah, I'm sorry. That wouldn't be k squared, you're right, because y is not squared. Good. Sorry about that. That should be just k, yeah. You're absolutely right. My fault. So here I put a k squared because, you know, I make mistakes. But it really shouldn't be k, right? Because y was never squared. So that's k to the first power. Thank you. Okay, now looking down at the x and y plane, we see initially on the x and y plane, we see this thing right here. And then looking from the left, we see a bunch of circles. And then looking from this at the YZ plane, we also see that. So putting those together, we must be looking at this kind of shape, right? Looking at this perspective here, changing the value of k, changing the value of x, means where I slice. So each of these will show up like that. If I choose an x that's, say, 5, for example, pretty close to us, then I'm seeing a parabola that doesn't have a vertex at the origin, because we have this three-dimensional shape and we're cutting from near the edge of it. Can you see that? Yep. So this is the kind of shape we're dealing with. And what do you think this is called? Paraboloid. Yeah, we're dealing with a bunch of parabolas, and then we add an oid to make it a three-dimensional thing. So this is, you're right, a paraboloid. Okay, one more shape, and this is the most complicated shape. Y squared minus x squared is equal to z. And upon first glance, this looks very much like the equation we dealt with last time. Y is equal to x squared plus z squared, right? Upon first glance, they look very much alike. Now the difference is here. In the last example, the squares were both positive. Here we have a negative here. So we know we have some kind of hyperbola going on. We don't expect a paraboloid anymore because we got some kind of hyperbolic thing going on. Go through the same process again with different traces. Z is equal to k, for example, we get y squared minus x squared is equal to k. We've seen this a gazillion times today. This is a hyperbola. A bunch of them. And depending on the value of k, it's going to change which axis the hyperbolas will intersect. If k is positive, then the hyperbolas intersect the y-axis. This is a positive k. A negative k means that the hyperbolas will intersect the x-axis. So I'll use dotted lines for that. So what this means is that if k is positive, we're talking about xy plane going up, positive z, positive height. If this projector here is the xy plane, we will see a bunch of hyperbolas coming up. But going below, the hyperbolas will be reflected to the other axis and going down. Does that make sense? Different slices of that. Let's look at y is equal to k. And I'm going to write it this way. Z is equal to negative x squared plus k squared. And these are what? Parabolas, right? And in the x versus z view here, which way do they open? Down, right. And k is going to change the vertex, right? So the smallest k can ever be is, smallest k squared can ever be is 0. And that would be 1 over here. And as we change k, k squared will be positive, of course, and that's going to make this go up. So something like this for k is equal to plus or minus 1, for example. As an example, plus or minus 2 will keep going up. So we have some kind of symmetry with respect to y is equal to k here. Plus or minus k, we see the same kind of shape. Some kind of symmetry. Last set of traces. X is equal to k. And we get a set of shapes very similar to y is equal to k. Very similar. We get y squared minus k squared for whatever k you want to use. These are likewise a bunch of parabolas. And in the y versus z view, with x coming out at us, positive y squared means these things open upward, right? In this perspective, they will open up. If k is equal to 0, we have z is equal to y squared. So it would look like this. And for any other value of k you use, minus k squared is always going to bring the vertex down. So for example, if k is equal to plus or minus 1, that parabola will be brought down to here. Okay? All right, now let's try to sketch this thing. This is very hard to sketch, so bear with me here. From the top looking down, we see hyperbolas that open either two, that's symmetric with respect to the y-axis, or symmetric with respect to the x-axis. The difference is whether you go above or below. So let me sketch this thing out, and we're going to take a better look at it. Oh man, I hate sketching this. This is really, really, really... You know what? I'll do it. It's kind of a hard one to sketch. And then this doesn't show up, sorry. Think of a saddle, right? The thing you put on a horse. or anything, or a camel, I guess you could do the same thing. But think of a saddle, right? You sit on the saddle, front and back, your legs hang out here and here. That's basically what we got going on here. Notice what happens if you look down. Above the x and y plane, we see hyperbolas that are basically these guys. For positive z, we see a bunch of hyperbolas. Now, when you go below the x-axis, below the z-axis, what we're seeing are hyperbolas that open the other way, kind of like these guys. And then the parabolas show up here, looking this view, and then also looking down like here. Okay, one last thing, the name of this thing. This is called a hyperbolic paraboloid. Right? You got a mix of these two things. You got a hyperbolic, kind of defining. Oh, I know. You've all eaten Pringles, right? This is exactly what they are, Pringles. Next time you eat it, take it out, take a look at it. That's exactly what we got. You're eating hyperbolic paraboloids. All right, see you Wednesday.